Right, I'm going to go over some physics questions to do with forces and matter. And these questions will be good for any exam board, particularly the Edexcel for Unit CP13 for the double award, which is called SP15 for the treble. And there's 23 marks up for grabs here. You'll see some of the questions are the same, and that's because I've took them off previous papers and put them all together. Question 1. The graph in figure 14 shows the variation in atmospheric pressure with the height above sea level. So there's height above sea level, atmospheric pressure. Use the graph to estimate the atmospheric pressure at 3,000 metres above sea level. So this is just a data handling question. Here's the data. Can you handle it? So I always just draw little lines coming along from the 3,000 in this case down onto the x-axis, and there's your answer, 70. Part 2. Use the graph to estimate the atmospheric pressure at 6,000 metres above sea level. Well, I'll just do exactly the same but for 6,000. So 6,000, come across. Now you can see this time it's not as easy, but it's probably somewhere between 46 and 48. So I'll say 47. Question 2. A weight of 4 newtons is used to extend a spring. The extension of the spring is 0.06. Calculate the spring constant K of the spring. Use that equation. F equals Kx. Right, well that 4 newtons there, that is your force. And there's your extension there, which is X from the formula. And we need to rearrange it to find K. So K equals F over X. Make sure you can rearrange equations. These are easy ways to get 3 marks from your equations. Pop the numbers in. And that equals 66.66 recurrent. Now I often get asked how many decimal places shall I put it to, and my answer is always the same. Do it to the greatest number of decimal places that they give you the numbers to. So that's to 1 decimal place, but that number there is to 2. So I'm going to give mine to 2 as well. And that'll round up to 66.67. Unless, of course, they say round it up to a specific number of decimal places or significant figures. Part 2. State what measurements should be made to determine the extension of the spring produced by the 4 newtons weight. Right, base your explanation on the calculation. So extension is the new length, take away the original length. So basically we need to measure the new length and measure the original length. Question 3. Another spring has a spring constant of 250 newtons per metre. So that's our K value. Calculate the work done, so that's the amount of energy, in stretching the spring by 0.3 metres. That's our extension. And state the unit. And just pop the numbers in. And that equals 11.25. And it's energy, so that'll be joules. Question 4. Figure 9 shows a 10 newton weight hanging from a spring. Once again, that's the force. You can always tell it's a force because it's got the units newtons. One of the forces acting to stretch the spring is shown in figure 9. Complete figure 9 by adding an arrow to show the other force acting to stretch the spring. So if something's going to stretch, you need a force pulling it up and another one pulling it down. This weight here is pulling it down. Now make sure that the size of your arrow is the same as that arrow at the top, roughly. And make sure they are in opposite directions. So equal in size, but opposite in directions. And I always put my weight acting from the weight itself, from the bottom of the weight, or there or thereabouts. Question 5. A student sets up the apparatus shown in figure 9. When the current in the solenoid is switched on, the solenoid attracts the iron nail. The spring constant of the spring is 24 newtons per metre. The spring is extended from an unstretched length by 12 centimetres. Right, we're going to have to convert the centimetres into metres. Let's just do that now. Use an equation selected from the list of equations at the end of this paper. So we need to calculate the energy. And we've got K and we've got X, so we'll use the same equation as before. E equals a half kx squared. And that equals 0.1728. Question 6. Figure 14 shows an athlete using a fitness device. The athlete stretches the spring in the device by pulling the handles apart. The spring constant of the spring is 140 newtons per metre. So write down what you know when you know it. So we know K. The athlete does 45 joules of work to extend the spring. So we know energy, or we know work. And the athlete takes 0.6 seconds to expand the spring. So we know time. Calculate the useful power output of the athlete when stretching the spring. Right, well, power equals energy over time. So we didn't need K, not just yet anyway. So if we put the energy in, divided by the time, and that equals 75. And power is always measured in watts. Part 2. Calculate the extension of the spring. Use an equation selected from the list of equations at the end of this paper. Right, so we've got the energy, we've got the extension. We'll just use the same equation as before. E equals a half kx squared. Remember, all these questions come from different papers. That's why it's the same questions coming up again and again. What they've done this time though is they've asked you to work out the extension. So you're going to have to rearrange the equation. Now if I know I'm going to rearrange the equation, instead of putting a half kx squared, I prefer to put E equals kx squared over 2. It just helps to rearrange it. I'll show you what I mean. Right, now I can just take the 2 and just pop it straight over there. And then if I divide both sides by K, K will end up over here. Now I don't want x squared, I want x, so I'll just square root both sides. Pop the numbers in. And that equals 0.80. Or just 0.8, because again, that was to 1 decimal place. That's the greatest number of decimal places. Question 7. A student investigates the stretching of a long piece of rubber. Figure 15 shows the apparatus to be used. The student puts just enough weight on the weight hanger to make the piece of rubber just tight. The student wants to plot a graph to show how the extension of the piece of rubber varies with the force used to stretch it. The student adds a known weight to the weight hanger. Describe how the student could measure the extension of the rubber when he adds another weight to the weight hanger. Right, so get the length with a ruler of the known weight. Add another weight on and then re-measure how long it's gone, and the difference is the extension. Because remember, the extension is the new length, take away the original length. So you're definitely going to get 2 marks for that. You can get anything up to 5 really. Last question, part 2. The student obtains a series of values of force and extension while loading the piece of rubber and then unloading it. Figure 16 shows the graph of the student's values. So they've popped the force up the side, the extension along the bottom. There's the graph as the rubber's being loaded, and as it's unloading it, it's coming down a different route. Explain how the shape of this graph shows that the distortion of the piece of rubber being stretched is different from the distortion of a spring being stretched. Right, well, a force extension graph of a spring looks like this. As long as you don't exceed the elastic limit, it's basically a straight line. Now when you load the spring, it's a linear extension, and then when you unload it, it goes back the same way. Whereas this, you can see for the piece of rubber, it's not linear. And as it gets unloaded, it doesn't come down the same route. So let's just write that down. You could also say that the rubber band is not directly proportional, unlike the spring, which is, because the spring is linear and it goes through the origin, which is 0, 0. Right, well I hope that's helped you when it comes to answering questions to do with forces and matter. There wasn't that many questions to do with matter on there, but I'll be making other videos, and the more videos you watch, the more questions I'll go over, the more you'll increase your success. Right, see you in the next video. Work hard, be nice. Bye for now.